So, good afternoon. It's time to start today's lecture. And today we are dealing with the last process-related topic during this course, and that will be bio-oils manufacturing and also upgrading to better quality fuels. We'll start with short introduction of pyrolysis and liquefaction, and here are some definitions of pyrolysis. So it's thermal cracking in the absence of oxygen. Pyrolysis is thermal decomposition of organic material at elevated temperatures in the absence of gases such as air or oxygen. So basically the biomass is treated at elevated temperature, and it breaks down because of the temperature, and biopolymers break into smaller fractions and more chemicals. Here's a video that explains a little bit, or it's an introduction to pyrolysis. If you are interested in it, so you feel free to check YouTube. Here is the same illustrated in terms of the biomass itself. So that will be heated to quite high temperatures. We'll take a look at some conditions and residence times and so on during today's classes. But basically only biomass is fed into the reactor. It's heated rapidly and it decomposes into vapor, and also it forms a biochar, which is a solid component. And the vapor at high temperature, so it contains so-called condensable bio-oil part and some light gases which can be combusted. Thinking about cellulose, the one main ingredient in biomass, so that's when heated, so it will break down into these different types of bio-oil components. You'll obtain also water, and here you'll see these combustible gases like methane, carbon monoxide, and also solid biochar will form as products. Pyrolysis forms also water, and that was the last on that slide. Advantages of this biomass pyrolysis, some very general things. This is carbon, one possibility to obtain carbon neutrality, and you can utilize waste biomass, which is preferred over some otherwise useful woody biomass. It can be self-sustaining energy-wise, so the light gases and the biochar can be burnt for energy and used for that pyrolysis process heat. This pyrolysis bio-oils have increased bulk and energy density, and these in principle can be used to manufacture or upgrade into valuable chemicals such as fuels. And fast pyrolysis of biomass has basically three main parameters that can be varied. And one is the temperature. Second one is how fast the biomass will be heated and how long these formed vapors will stay in the reactor. With the biofuel context, so the objective is to maximize the liquid fraction, product fraction. And this can be done by applying moderate temperatures. In pyrolysis, moderate temperature can be somewhere around 500 degrees Celsius. Short residence times for vapor also are required, and I have few slides about that with respect to the product yields. Here you see different types of treatments: fast, slow, and gasification. Gasification we dealt last week. Fast pyrolysis, we look at the parameters later as well, but it's the residence time it's much shorter in the reactor, and this is very rough product yield. So here you'll see liquid, the char, the biochar, and the gaseous components. So in gasification, the last row here, so the main product is gas, and typically the synthesis gas that we discussed last time. Then on the other side, there is the fast pyrolysis with moderate temperatures. So there the main product is liquid components, and gas and solid ones are quite small. And then the slow pyrolysis is mainly used for production of biochar, and that's formed not as an only product, but in any case, so that's one of the largest products that are obtained in a slow pyrolysis process. Here's some kind of flow scheme of that reactor one type of reactor setup that can be used. So it's here you'll see the actual reactor, the fluidized bed, where the biomass is fed after some pre-treatment steps. Here it's like drying and grinding it to small enough particle size that it works in the fluidized bed reactor. Then there is a gas flow from the bottom, and the reactor and the hot gas is heating the biomass, and vapors exit in the cyclone, where the solid char and the vapors are separated. Then after cooling, the condensables are obtained as bio-oil product, and the gaseous material, non-condensable gases, can be used. These are combustible, so it can be used for heat for the drying, and or for heat for the pyro process itself. This graph is yield versus reaction temperature. So you'll see that the red line here represents gaseous components. So with increasing reaction temperature, gaseous components tends to increase. With the desired green liquid products, there is some kind of optimum for the maximum yield. So one has to play with the reaction parameters to get most of the desired product. Here is yield again, but with the residence time. So it's roughly how long the material stays inside the reactor. And as you see, the residence times are quite short in the pyrolysis. So here you see 2.5, 5, and 20-second residence times, and also how it influences the liquid, gas, and solid product yields. And in accordance with the previous slide, so same as temperature increase, so also residence time increases gases. Lower residence time favor the formation of liquids clearly. If there is a very long residence time, you'll obtain decreased amounts of liquid products. In this curve, solid yield doesn't change that much, but there is a trend that longer residence time results formation of higher amounts of solid products. And here are these kind of discussion questions which I have used during the course sometimes. So there is a kind of a question that the liquid produced in pyrolysis are non-thermodynamically controlled products, and what this means. So the idea would be that you'll discuss or think about it yourself. Here are some answers to that question. And basically, at low temperature, reactions are under so-called kinetic control. And the major products are those that form from fastest reactions. But at higher temperature, the reaction is under thermodynamic control. So in other ways, the product is the most thermodynamically most stable. So basically, if one wants to understand this in another way, so at higher temperature, reaction rates are so high that all reach the thermodynamic equilibrium, and then the product mixture is determined by thermodynamic control. But at low temperature, reaction rates are slower, and the product distribution doesn't reach the thermodynamic equilibrium composition, and therefore it's somewhere called that it's under kinetic control. And pyrolysis happens so fast that the product distribution, the liquids and so on, are not thermodynamically controlled. Here's another explanation what it means, but this is more physical chemistry side, so I will not go into details. It's the same thing described in a, let's say, another way. So basically, equilibrium constants can be calculated for reactions based on theory and thermodynamic data, but often these rate constants, which are related to reaction rate, cannot be calculated, but those are based on experimental evidence. But Then the course book describes two main bio-oil production methods, one being liquefaction and the other being pyrolysis. And what's the difference in those? So pyrolysis oils are water soluble and have high oxygen content or higher than the liquefaction oils. And on the opposite side, so liquefaction is another type of process of treating biomass, and it produces water insoluble bio-oils. So there is a clear difference. The process conditions vary in that terms that liquefaction happens at higher temperatures, higher pressures and lower temperatures, whereas pyrolysis is the vice versa. So the pressure is low and temperatures are higher. We have more material on both of these coming shortly. Pyrolysis has lower capital cost because of the lower pressure requirements. So if you need to have high pressure equipment, so those are much expensive than the low pressure ones. So there is the main factor behind of this difference. Typical characteristics and properties of pyrolysis versus liquefaction, and the course book contains most of these tables and slides materials that I show here. And here you can compare like typical properties of pyrolysis oil, liquefaction oil, and the heavy fuel oil, which is fossil-based product. And the elemental compositions with pyrolysis oil and liquefaction oil vary to some extent. So liquefaction oil has clearly higher amount of carbon, which is good. That's the one element that we want in the fuel. And on the other hand, pyrolysis oil has a lot of oxygen, which is not the desired for fuel. And that partly comes from the different water-soluble components, making the pyrolysis oil water-soluble, whereas the liquefaction oil is insoluble to water. Also, other parameters vary here. Pyrolysis oil has moisture or the water quite a lot, whereas liquefaction oil has much lower amounts. Advantages that can be found for bio-oils. So keep in mind that bio-oils can be made with pyrolysis or liquefaction, or you can talk about, if you want to specify the method, you can talk about pyrolysis oil and a liquefaction oil, but generally these are both bio-oils. The benefit here is that bio-oil production requires only a single reactor, and a large fraction of this biomass energy can be converted or contained in that formed liquid product. Also, very different types of biomass feedstocks can be used, and the reactor is not that picky or sensitive regarding that. And there were some ideas how the process would be organized. So since the bio-oil reactor setup is fairly simple, so I have at least heard about ideas that there would be these smaller reactors closer to the site where the biomass is formed, because that can be treated on site, and then the energy intensive bio-oil could be produced into bio-oil refineries where those fancier upgrading steps could be done. So this enables this cheaper transportation of biomass. In the bio-oil is already condensed. If we compare it to the biomass that can contain 50% water. So this is one possibility, that there are small distributed bio-oil production reactors which produce oil that will be refined in one single large refinery. Disadvantages are also in bio-oils. So in terms, if we think about bio-oil as a fuel, so there are lots of problematic features. So poor volatility, high viscosity, coking tendency, it's corrosive, and also cold flow problems. It comes partly from the viscosity, and it's too viscous at low temperatures. And also, I think, although this textbook is 20-year-old, so I think there aren't yet really any standards for the bio-oils, and that's what we discussed in the first part of the course, that the standards are very important to guarantee that the material or the fuel is of stable quality, or it fulfills the standard requirements. Main concerns with using bio-oils in diesel engines is the difficulty of ignition, the corrosion and coking, and due to these disadvantages, so it's very often that bio-oils must be upgraded. Last, on the disadvantages side of bio-oils, one can say that the bio-oils can form polymeric structures and can condense during the storage. So these are not oils that can be stored very long times or lengthy times. So, and these degradation or side reactions are accelerated by increase of temperature, exposure to oxygen, and also if UV light can reach the container contents, so it degrades the bio-oil quality. Here's a YouTube video about fast pyrolysis, so take a look if you are interested. Some properties of fast pyrolysis. So this graph I already showed. So here is a process flow sheet of fluidizing gas pyrolysis reactor. So it's very simple in that sense that there is only one reactor, quite simple pre-treatment step, and then just few separation or recovery operations. Here the cyclone that separates solids from the vapors or liquids, and then solids from the gases, and then the gas liquid separator separates the bio-oil and the light gaseous components obtained from the pyrolysis reactions. There are different types of reactors for for pyrolysis, fluidized bed, circulating fluidized beds, and also ablative pyrolyzer and vacuum pyrolyzer. These all have been explained to some extent in the course textbook, and I have few slides about this. Here are some advantages and disadvantages, so I will not go these into details through because you can read those also yourself. Here, only thing that I can note that for this type of reactors, so the biomass has to be ground to quite fairly small powders or small particle size, so from 2 to 3 millimeter diameter. I think this is more or less the same what we already saw, the reactor setup. Fluidized beds, so the heating of the biomass happens through conduction of the reactor walls and also with the help of that fluidizing gas that is pushed from bottom all the way through the reactor. Circulating fluid bed is slightly different, so that the fluid beds it's that the operating principle is slightly different there. There is the char residence time is almost the same as the vapor and gas residence time. The hydrodynamics of these circulating fluid beds are rather complex, but they can produce high throughputs of processed biomass. And in this, the heating is supplied by recirculation of heated sand. Here's circulating fluid bed reactor setup. So it looks fairly similar as this fluidized bed. Here the biomass enters the pyrolyzer reactor. What is different that hot sand is fed into the reactor. The same sand is recovered at the cyclone where the products leave from the top, and the sand and also the solid char from the bottom. And these are combusted in another reactor where of course the char component burns and it produces heat, heating the hot sand, which will re-enter the pyrolyzer reactor and heat the products inside the reactor. The liquid or the product separation happens then in this quench cooler and electrostatic precipitator parts. So one obtains here the desired product, bio-oil, but you also get, like in that fluidized bed pyrolysis, so the gaseous components, that light gaseous components that in principle can be burnt to produce energy or heat for that process or for other purposes. The ablative pyrolyzer was the third type of reactor, and there the heat transfer comes from the hot surface, so the setup is somewhat different. And I think I have better picture. So there is this kind of rotating part which has this blue, I don't know what these are called in English, but in any case, so the biomass is pressed with these paddles against the hot outer wall of the reactor, and there the heat is supplied for that pyrolysis process. This picture maybe tells better picture. So these are okay. So here these are called blades. So these blue things that squeeze the biomass against the hot wall are blades, and this is kind of an enlarged image. What happens is that the blade is pressing the wood chips against the hot metal wall, and then the heat comes from that hot wall and causes this pyrolysis reactions to take place, and the products can be are formed in that way. Vacuum pyrolyzer was that fourth reactor type, and it has advantages like very short residence time for the volatile components and longer residence time for the solids. So it allows more balancing between the solid and the gaseous liquid components. So maybe minimizing the amount of solids and maximizing gases and liquids. If there is a vacuum inside the reactor, so the disadvantage is that in vacuum the heat transfer and heat transfer is rather poor, so that can be challenging. Here's a collection of these different types of reactors. So if you are interested, so you can take a look and study these further. Here are different categories like technologies that are in commercial use and some which are only at laboratory scale. So here are some operating conditions still, just to get an idea, like if we discussed more like this fast pyrolysis and conventional pyrolysis, so in that fluidized bed reactors and so on, the residence times are in the order of some seconds, not like minutes or hours like in the slow pyrolysis reactors. And what we are interested in is of course the liquid products. So here you'll see which processes produce mainly liquids, and those are this flash or fast pyrolysis and vacuum pyrolysis, pressurized hydropyrolysis. But the temperature range so can vary, but here it's to get a kind of a feeling. So it's somewhere around 400, 600, 800 degrees. All these parameters can be also varied and fine-tuned for specific use. But there is the the heating rate. So that depends what we little bit went through in connection to those different types of reactors, so what they are capable of. So high heating rate, medium temperatures, and short residence times favor the formation of liquids suitable for fuel production. Main products and side products, energy waste recycling. So this already was touched a bit, but there the biomass that is fed so into the pyrolysis reactor, so it forms this solid, liquid, and gaseous products, and the light gases can be burnt for energy. Those can be used for heating, for example, because that is used here. The bio oil itself is the main product, but then the char, solid carbon, is side product, but that can also be burnt for energy. So there are kind of side products that can be used, or one could say that the energy in the energy is kind of recycled. But this we already went through some time ago. Liquefaction process. So previously those reactors were pyrolysis. This is about liquefaction, and here high temperature is the key to the liquefaction. And so what liquefaction is, in the pyrolysis there were basically only the biomass and then the heat that is applied. In liquefaction, so there is the high pressure gases and catalyst that are employed to make a higher quality liquid product, and there is also there can be used a solvent and reducing gases like hydrogen, carbon monoxide, and the catalyst. So this is basically a reactor that you have the biomass, then you mix it with some solvent, introduce hydrogen or reducing agents which remove, for example, oxygen impurities, typically with the help of a catalyst. So this is kind of a more demanding process. If you utilize the solvent, aqueous solvent, so water, so you can talk about hydrothermal processing. If you don't have any solvent, so you can talk about hydropyrolysis. And if you have a reactive solvent, so that could be some base or acid, so then talk about solvolysis process. And whenever you applied molecular hydrogen, you need a certain catalyst, because molecular hydrogen as such is very inert. Nothing happens, or it's not reactive if we exclude combustion. So it requires the catalyst for it to do something good. And solvolysis utilizes solvents like creosote oil, ethylene glycol, or certain alcohols and phenols as solvents. Some examples of those. So the hydrothermal upgrading or hydrothermal processing is treatment with hydrogen and the bio oil itself. So that's one example where it can be applied. Here's a process flow scheme of this type of hydrothermal upgrading process. The catalysts that are used in liquefaction of biomass so are alkaline, typically different types of metals, or then these supported nickel and ruthenium heterogeneous catalysts, which enable hydrogenation reactions. These alkaline catalytic materials break the biomass into different chemicals. The same with this another type of metallic catalysts. And regarding the solvents, so of course water is the most attractive due to its low cost. Another thing is that biomass has always some amount of moisture. So if you use water as solvent, so you don't need to dry the biomass before before the liquefaction process. So that makes sense to use water. Few words about the different reactions that take place while processing or while producing these bio oils. So there are a lot of reactions taking place because, well, there are also like hundreds of different molecules or products which can react, which can break to different molecules, and the formed molecules can react with each other. So this is just a list of some examples like hydrolysis, dehydration, isomerization, dehydrogenation, aromatization, retrocondensation, and coking. And what these reactions form, so you'll see here a very broad range of different products. So acids, esters, alcohols, ketones, aldehydes, oxygenates, sugars, furans, phenols, and so on. Really complicated mixture of these are just type of organic molecules. Then there can be like tens of different acids or esters and so on. So quite complicated mixture. But on the other hand, if you compare bio oil to fossil-based crude oil, so the crude oil that is used, so it also contains hundreds of different organic molecules. So in that sense, the bio oil is not exceptionally complicated, but it's closer to the crude oil composition in that sense. Chemical composition of the products made by liquefaction and fast pyrolysis. So this picture I already showed. But this was the one that I wanted to show you again. So we glanced this already through, but keep in mind that pyrolysis oil is this water-containing, water-soluble composition. So in order to organic materials to be water-soluble, so they usually have to have like oxygen functionalities, like alcohol or something like that, carboxylic acid, and that comes from the what I already showed you, that here is like the elemental composition is very high in oxygen, and that boosts the water solubility. Also, liquefaction oil has much higher heating value compared to pyrolysis oil, and it's nearly comparable to the fossil-based heavy fuel oil. So in summary of these, liquefaction and pyrolysis are the two major techniques to produce these bio oils, and liquefaction and pyrolysis oils are, as we just saw, so are or have a different composition, but one key observation is that the majority of these bio oils are of low quality or poor quality for fuel applications, and those require some processing or upgrading in order to be used in let's say in diesel or gasoline engines. And this typically these bio oils are used in as a boiler fuel or in power and heat production, and in some cases also for making of chemicals, but that's of course could fall into this upgrading category. So if you process the bio oil further, so you can make valuable chemicals or fuel components. Bio upgrading material can be found in the course textbook. That will be the chapter 6 that covers these topics. And some of these techniques that we go through, so there is a lot of new information and research on these since the textbook was written. So, but the main principles and ideas come clear, and that's the purpose of this course as well. If we take a look at this valorization pathways of lignocellulosic biomass, so here we have been dealing with pyrolysis and liquefaction. And if you take a look at this process scheme further, so these primary products that we discussed, like pyrolysis oil and liquefaction oil, so in this scheme, so those are both upgraded here with hydrotreating and refining in order to get useful products, and the same in liquefaction, so treatment with hydrogen and refining it further to get the products. So then we get closer to value added products, useful chemicals and so on. So these products that are obtained from the pyrolysis are not that useful as such, but the let's say the volatiles can be used to produce heat for the process, and the same with the char. And this pyrolysis, this oil or the condensable part will be processed or upgraded further. So the motivation for the upgrading is that the pyrolysis oils are quite poor quality chemicals in terms of fuels. So there's high oxygen content that is not desired for fuels, because you want fuel that has low oxygen content so that it can combine with oxygen molecules and combust or burn, produce energy. So if it already has oxygen, so it has lost some of the energy production potential. These are immiscible with petroleum products, meaning that these will not mix with the petrol, gasoline or diesel. So these are water soluble, meaning that they don't dissolve into the typical organic fuel components. And this we already also mentioned earlier. So these chemicals, bio-oils are unstable in terms of stability. The stability is low because they undergo side reactions like coke formation, and also they can form larger polymeric structures, which are not desired things for a fuel component. The composition is somehow illustrated in this pie chart and also in the table. Table contains the elemental composition and water content. And on the other hand, this pie chart describes what different type of molecules are involved. So acids, alcohols, aldehydes, sugars, water, and different high molecular weight, low molecular weight lignin, and also the extractives. The extractives where this oil organic soluble, like the other opposite to the water soluble parts. So these extractives will easily dissolve into organic matrix. But in any case, so the motivation is that this can be improved. As such, it's not very useful product. We would like to have low oxygen content, low viscosity, low molecular weight, high aliphatic content. Aliphatic is the opposite to the aromatic. So if you have aromatic components like benzene and these lignin type monomers, so those are aromatic, and everything else is aliphatic. That comes from the fuel side. It's not very well defined in chemistry what aliphatic is not used in chemistry, and low coking tendency is also desired. So product here is a small plastic container that shows how the biofuel looks like. So it's not very clean looking material. This is the same disadvantages that we already went through, I suppose. Is there something that I should maybe highlight still? Maybe not. So this is something that you cannot, you don't want really, that if you have the bio-oils, the thing is that there are so many different types of organic molecules that are quite reactive. So there are acids and aldehydes, ketones and alcohols. So those can easily react with each other and form secondary products or polymers just by being in contact with each other. And if you increase temperature, usually the side reactions and all type of reactions tend to become faster. Oxygen exposure also promotes oxidizing reactions and so on. And very often, if there is exposure to ultraviolet or direct sunlight, so it can catalyze or enhance these reactions as well. So the disadvantages can be or are for a low heating value. So there is a lot of water and not so high heating value components inside. It's incompatible with conventional fuels, so it cannot be used as this drop-in fuel because it's chemical-wise very different. Also, it's problematic when it contains solid material. If it has too high viscosity, the volatility is too low to work, ignite well, and also this chemical instability is problematic. The course textbook focuses into 4 different upgrading techniques. One, which is the hydro treatment. So then second is the upgrading using these zeolites, which are kind of acid molecular sieves, often acidic materials. Third is the making kind of blends or forming emulsions where you mix the bio oil and the conventional diesel fuel. And the fourth one is something that we already studied in the gasification part last week. So it's also possible to process the bio oils by steam reforming and produce synthesis gas. And then all the routes that come with the synthesis gas are also possibilities. So hydrodeoxygenation, or HDO acronym. So it's basically hydrogenation reactions. So you have high pressure hydrogen in the reactor where the hydrogenation suitable catalysts are for hydrogenations and high temperature. And basically what happens is that the oxygen atoms are converted with the hydrogen and catalyst into water. So the oxygen functionalities are removed from the hydrocarbon structures. And also if there are unsaturated, so carbon double bonds, triple bonds, so those are saturated to single bonds. So the hydro treatment makes the bio oil various chemicals like closer to fossil fuel hydrocarbons. That's the idea. So this is what happens there. It's the same thing that already explained. So the pyrolysis oil enters the deoxygenation reactor or process, and you need to feed hydrogen into the system. So basically the biomass bio oil components react with hydrogen. You get the desired hydrocarbons, and as a side product, one could say you get water, carbon dioxide, methane, and carbon monoxide. So this upgraded oil is the better quality fuel component, whereas the water and the gaseous components are removed after this hydrodeoxygenation treatment. Here is just a scheme of a normal reactor. and there is basically nothing else. Why I wanted to have this here is that here are there is the catalytic material, ruthenium on activated carbon. One needs to have the hydrogen reactant, so hydrogen gas, and the bio-oil hydrodeoxygenation takes place in this reactor for quite long time, so it takes hours to complete the hydrodeoxygenation process. And the typical conditions, so these are quite high temperatures, but not uncommon for petrochemical industry. But in any case, so 400 degrees Celsius, and I would say that fairly high hydrogen pressure, so like 200 bars. I think this batch autoclave of 5 liters will not. It refers to laboratory scale experiments in a way. So but I think that we can forget. Products that are obtained, so one can, after hydrodeoxygenation, one can get this oily phase, which is the fuel component, then the gas phase, which is contains light hydrocarbons that can be burnt, aqueous phase, and also some water. The good things come with this hydrodeoxygenation process is that the energy content of that obtained fuel is significantly higher, and also the stability of that fuel is much better, because this several active organic molecules are removed or converted into regular hydrocarbons, which are much stable than the alcohols, aldehydes, ketones, carboxylic acids that are removed by this treatment. And also the increase in viscosity takes place during this process. For this hydrodeoxygenation, so commercial sulfide coupled molybdena or nickel molybdena based catalysts are used. And this is not any surprise that these are the same type of sulfide catalysts that are also used for hydrodesulfurization, removal of nitrogen, and also removal of oxygen in the petrochemical industry. So the catalytic materials and the process conditions are close to each other. So hydrogen is applied or utilized to remove oxygen, nitrogen, and also sulfur. So these all these removals with the hydrogen improve, let's say, the fuel quality when it removes oxygen or nitrogen, and also like the exhaust gas quality, that once the sulfur is removed, so it will not cause sulfur dioxides, and that's good also for the environment. Here is the difference between the bio-oil being processed and how it changes after the after the hydro deoxygenation process. So carbon content increases, also oxygen content decreases, and the same is for the water content. The higher heating value nearly doubles after this treatment. Here are more parameters that have been compared, like properties of bio-oils and upgraded bio-oils. So the first one here is liquefaction oil. The middle column introduces the pyrolysis oil, and then on the right hand side it's these hydrotreated oils which have been upgraded, and you'll see significant changes in quite many important parameters here. Then a few words about the zeolite upgrading. So we went through zeolite materials in connection to the catalytic materials. Some zeolites can be found in nature. These are the kind of clay type minerals that have this porous microporous structure, so tiny channels and well-defined crystalline materials. And these were often the typically zeolites that are used in this type of applications are acidic zeolites. So those have very strong acid character, but those are solid materials. So they can promote acid catalyzed reactions. And this acid functionality is important for quite many petrochemical industry reactions, and that's why zeolites are used frequently in oil refining, petrochemistry, and production of basic chemicals. In this zeolite upgrading, 350-500 degrees Celsius is applied at atmospheric pressure, which is good because it doesn't require high investment cost for that reactor. The products that are formed from that bio-oil are listed here. So hydrocarbons, which are typical fuel components, some water-soluble organics, oil-soluble organics, and also light gases and coke. Dehydration, cracking, polymerization, deoxygenation, and aromatization reactions happen during this zeolite upgrading process. The advantages of this method to apply zeolites at high temperature, at low pressure, so it improves the quality without the need of hydrogen, and the pressure is low. It reduces the operating cost. Temperatures are similar to those that are used normally for bio-oil production. So this, in principle, could offer economic advantages over these hydrotreating upgrading. There are disadvantages, and the hydrocarbon yields are quite low that are obtained from zeolite upgrading. Also, zeolites, that is linked to the property of a zeolite, so coke formation is quite high. It's very often when dealing with zeolites, so the zeolites as catalyst, so the acid functionality also tends to promote coke formation, and that causes problems. Here is also like related to the coke formation, so quite a lot of the bio-oil will be deposited on the catalyst as a coke or in the reactor as char. So this is something that should be taken care of. Like coke deposit on the catalyst will also lower the catalyst activity and deactivate the catalyst. For example, in oil refinery, in these crackers where they use catalyst, so catalytic cracking, so there the catalyst lifetime is just few seconds because of that coke formation. So there is kind of the catalytic reaction and a continuous catalyst regeneration where the coke is burnt out from the zeolite, then it enters again to the reactor for a few seconds, and then it exits enters the regeneration stage again. So this is typical for these acidic zeolites. These are just some model compounds for that upgrading with zeolites. So here you see alcohols, propanol, butanol, and you'll see a ketone, acetone. So you can get, with the zeolite treatment, you can get like products like paraffins, aromatics, then ethene, butene, roughly similar products also from butanol and from propanol, which has 3 carbons. So you get propanes, butenes, ethene. So different hydrocarbons. And what is noteworthy is that these alcohols and ketones all contain the oxygen functionalities, but these obtained products in this site so have no oxygen functionalities. This is a comparison of different types of zeolites, so I think it's clear that there are, like I mentioned, so there are some few tens or hundreds natural zeolites, and then one can synthesize those in the laboratory, and some are better than others for certain applications. So this HZSM5, the H refers to the acidic form of that zeolite, and ZSM5 is the zeolite framework. There are also like other types of zeolites, but I will not go into the details of these characteristics. But just that you will not get an idea that all zeolites that are applied would be this ZSM5. So there are several others that are used. Then the last upgrading technique after zeolite upgrading is bio-oil mixtures. And here, this is close to the analogy of blending fossil fuels with biocomponents. But here the problem is that if you want to blend bio-oils with fossil-based diesels, so these two components or these two types of oils, diesel and bio-oil, are non-soluble with each other. And then one needs to apply additional chemicals to make mixtures, like you need to emulsions. You mix oil and aqueous phase with each other, and that cost money, but that can be used in some cases. So the bio-oil emulsions have improved characteristics. But the drawback is that the surfactants are expensive molecules, and on the other hand, the good thing is that there are surfactants, commercial surfactants available that work. But in any case, so that's a kind of a brother to this blending, so forming mixtures and then increasing the biocomponents in the fuel. But just as an example. Here's the cetane numbers of these bio-oil mixtures. If you decrease the bio-oil concentration from 46 to 34, sorry, now the cetane number changed from 46, which is the fossil-based diesel, by increasing 38% of bio-oil component into 34 cetane number, and in principle it's mentioned that cetane number between 40 and 55 are acceptable in normal diesel engines. So therefore one could conclude that you might form bio-oil emulsion mixtures with some 10 or 20% bio-oil content, and those would be acceptable still. And the last upgrading method treated in this textbook or in this context it would be the steam reforming of bio-oils, and this is a potential application. And this is something that I already tried to describe in the introduction, so that the bio-oil production technology could be applied so that there is a number of smaller pyrolysis plants which are technically simple for forming bio-oils, and then these bio-oils would be economically feasible to transport longer distances to large centralized biorefinery or regular oil refinery, where these bio-oils could be upgraded and used for making of bio-based chemicals, bio-based fuels. And one route for that could be the synthesis gas derived fuels. So the bio-oils would be converted to synthesis gas, and then to possibilities would be hydrogen, methanol, or even these Fischer-Tropsch hydrocarbons that we discussed last week. Also, one can consider this steam reforming of the side products, these solid carbon materials. So one can convert those in a very similar way as we dealt in that gasification last week's slides. So one can here alternative application for the chars would be as a solid fuel for production of heat, that we have, or I have mentioned already multiple times, that it's used in those processes and can be used. This I will not comment if it's relevant or not, but also in the zeolite upgrading, so you can use steam reforming to regenerate those zeolite catalysts in the very same way that you would produce here synthesis gas. So you can kind of process that coke deposited in those and see that as an upgrading or some kind of technology to utilize the solid carbon. Here are some process thermal efficiencies for different upgrading routes. And if we just take a look at, this is the starting material. So when you go to better and better products, understandably so, from pyrolysis ore to partially hydrotreated to crude hydrocarbons and refined hydrocarbons, so you tend to decrease the process thermal efficiencies, decrease when you make it more and more upgraded, more and more refined. But in any case, here you have information about how much of the actual energy is stored after processing these into more suitable fuels. So that's of course of key importance. If the process thermal efficiencies drop to very low values, so it becomes economically unfeasible for processes to work. So short summary about the bio-oil upgrading. So hydrotreating, so treatment with hydrogen, it's commonly done in oil refineries to remove oxygen, sulfur, nitrogen functionalities, and that can be also used to the same similar or very same technique, and catalyst can be used to upgrade bio-oils into better hydrocarbon fuels. Zeolite upgrading we discussed shortly. The good side of that is that it doesn't require the molecular hydrogen that is used in the hydrotreatment. So you only need those bio-oils and zeolites, and high temperature and low pressure is sufficient to improve the hydrocarbon content and composition. Bio-oils can also be converted to emulsions with diesel fuel, and this enables to increase the bio-oil content in that diesel without sacrificing the cetane number and the performance of that fuel very much. And then fourth alternative or opportunity is the steam reforming of bio-oils and that is part of that synthesis gas production, where you, and instead of whatever biomass, you can use that gasification of that solid carbon or bio-oils and convert that to synthesis gas, and once you have carbon monoxide hydrogen mixture, so there are various possibilities to make chemicals and fuel components out from those.